All right, everybody, we're back here for part two, which is where we're going to go ahead and start chapter 8, which is titled haloalkanes. And one difference about this chapter is instead of haloalkanes being our starting materials of this chapter, they actually are the products. So we're basically going to learn 3 new ways to make haloalkanes. And, there's only actually 3 reactions in this chapter, but we're going to introduce a new reactive intermediate, specifically free radicals. And so we have a lot of details to take care of in the front end to be able to go ahead and talk about these free radical reactions. Okay, so before we actually jump into the reactions, I just want to introduce haloalkanes as a functional group. We've already talked about the naming of haloalkanes, so we don't need to do that, but I do also want to mention the classifications of haloalkane, as being primary, secondary, allylic, benzylic, just to see how that, corresponds for haloalkanes. Okay, so here's the generic structure of a haloalkane. So we have an sp3 hybridized carbon bound to a halogen. And so we can have these R groups, where the R groups equal either hydrogen or an alkyl group. Okay, so X we're going to realize is the halogen, fluorine, chlorine, bromine, or iodine. And then again, R can equal H or an alkyl group. All right, so as I mentioned, what we're looking for is a halogen bound to an sp3 hybridized carbon. Remember that the carbon-halogen bond is polarized so that we have a partial positive charge on the carbon. We'll see how that's important in chapter 9 when we consider haloalkanes as electrophiles and what we can do with them as electrophiles. And so, as I mentioned, I want to revisit classification of haloalkanes quickly, and then we'll start to introduce the reactivity that we're going to see in this chapter. Okay, so classifications of haloalkanes. So using the terms primary, secondary, and tertiary, I think we actually already went over, so I'm just quickly going to rewrite those out. So if I have a methyl group attached to a halogen, that would just be a methyl halide. Okay, if I had the carbon that's bound to the halogen bound to one other carbon, that would be primary. Or if that carbon was bound to 2 other carbons, that would be secondary. Or finally, if that central carbon that's bound to the halogen was bound to 3 other carbons, that would be a tertiary halide. Okay, so that's classification is the same as what we learned for alcohols, and we're going to realize why that's important in chapter 9, because we'll learn that a few of the reactions can operate on methyl or primary halides, and a few of the other reactions can operate on tertiary and secondary. And so being able to accurately assess the classification of the halide is going to allow us to think about those reactions a little bit better. All right, and so I also want to talk about these ones, which would be a vinyl halide. Okay, so a vinyl halide with a halogen is attached to the carbon of a carbon-carbon double bond, and that's different than an allylic halide, because notice there's this intervening CH2 group there. Okay, so vinyl versus allylic, there is a different, in vinyl, the halogen's directly attached to the carbons of the double bond. In allylic, there's one carbon in between. Okay, and so we have a similar thing for benzene. So we could have an aryl halide, wherein the halide is directly attached to one of the carbons of benzene, or if we have an intervening carbon between benzene and the halide, remember that to be called benzylic. Okay, and I think we introduced these terms when we were talking about carbocations, so we're seeing them again here, but for the purposes of haloalkanes. Okay, so as I mentioned, what we're going to see in this chapter is we're going to learn of 3 different ways to make haloalkanes. But before we jump into the reactions, we need to address a different type of mechanistic arrow that we're going to encounter in this reaction. Okay, so every mechanism arrow and even resonance arrow that we've drawn to this point, every arrow is demonstrating the movement of 2 electrons. Okay, so there's actually another type of electron or another type of curved arrow where we only move 1 electron at a time. And this allows us to think about free radical reactions and free radical intermediates. Okay, so what we're going to talk about is the different ways mechanistically we can show the basically bond breaking process. Okay, so we're just going to say in general, a CX bond can be broken in 2 general ways. Okay, so the first way is the way that we've already seen before. This is called heterolytic bond cleavage. Okay, so I'm introducing this new term here, but we actually, hopefully when I draw the curved arrows down below here in a second, you'll be able to think about what the products of that curved arrow mechanism is because we've already seen this type of arrow before. All right, so I'm just going to take this generic alkyl this carbon X bond. It doesn't really matter what X is. Okay, so we're going to call this methyl group attached to X. Okay, so I want you to imagine that we used this curved arrow. Okay, so we're going to break the bond demonstrated by that curved arrow. So that curved arrow is telling us that we're taking the 2 electrons contained within the carbon X bond and we're giving them to X. Okay, so what is going to result as it relates to the carbon? Okay, so is the carbon going to bear a negative charge, a positive charge, or is it still going to be neutral? Okay, so hopefully you came up with the answer of, well, it's going to be a carbocation. I just took electrons away from that carbon. Okay, and then as it relates to the X, that becomes X minus. All right, and so that type of curved arrow mechanism we've seen where we're moving 2 electrons at a time. Here was one example. Okay, so for heterolytic bond cleavage, what we're seeing is both electrons contained in the CX bond go to the X, okay, in the mechanism. All right, so basically what I'm saying here is that both electrons contained within that bond are traveling in the same direction to the same atom. Okay, well, is there an alternative? So there is, and it's called homolytic bond cleavage. Okay, and here we're actually going to separate paired electrons, and this is how we are going to arrive at these free radical intermediates that I've been alluding to. All right, so I want to draw that same carbon X bond and think about the way we're going to demonstrate this homolytic bond cleavage. So we are going to separate the 2 electrons of the carbon X bond. Okay, and so how we do this is with a single pronged arrow. Okay, so let me draw it, and then down below I'll say a little bit more. Okay, so notice how those arrows are different. This would be a single prong. Single prong means we're moving 1 electron at a time, whereas a double prong or 2 prong equals 2 electrons at a time. Okay, so notice up here, I am basically taking 1 electron within the bond and moving it to carbon and taking another electron from that bond. So now that's 2 total and moving it towards the X. So I've separated those electrons and they're going to different atoms. One's going to the carbon, one's going to the X group. Okay, so what is the product of that? So we've unpaired an electron now. So now I have a carbon with an odd number of electrons around it. And then if I was going to show lone pairs on this X group, notice how I have a single unpaired electron. All right, so right here, and so we have an unpaired electron. So right there and right there are unpaired electrons. Okay, these are called radicals. So this would be a carbon radical. And this would be, if it was a halogen, this would be a halogen radical. So the reactions we're going to learn in this chapter are going to deal with radicals. Okay, so what is a radical? Okay, so you might have heard this before as a free radical. So you can call it a radical or a free radical, same thing. And so this is going to be any chemical species that contain 1 or more unpaired electrons. Okay, so any chemical species that contain 1 or more unpaired electrons. Okay, so we can see in the case of, the carbon radical and halogen radical, each of them has 1 unpaired electrons. Okay, so let's just, finish that up by giving a descriptor for that homolytic bond cleavage. Okay, so the 2 electrons contained in the CX bond go to different atoms. Okay, so 1, 2, C, 1, 2, X. All right, so that would be homolytic bond cleavage. All right, and so homolytic bond cleavage is the type of mechanistic arrows we're going to see in this chapter. Okay, so just a few, to re-highlight some of the important features here. So we're using a different type of curved arrow. These have a single prong that's telling us we're moving one electron in that direction that we're pointing to. That's different than the double prong 2-electron arrows that we've used in the past. And then the second thing is we're going to be dealing with radicals, both carbon and halide radicals, and for that reason, we'll have to spend, a considerable amount of time talking about, what controls the stability of free radicals. Okay, so let me introduce the first reaction. Okay, so this first reaction is noteworthy for a lot of reasons. One, because it's our first free radical mechanism and reaction we're going to consider, but also because this is going to be, I think, in both organic 1 and organic 2, it's really the only reaction of alkanes that we learn. Okay, and so this reaction is called free radical halogenation. So free radical halogenation. And what we're going to see here is we're preparing haloalkanes. So this is going to give us the preparation of haloalkanes. Okay, so as I mentioned, this is one of the only reactions that we are going to learn that starts with an alkane starting material. So we're going to take an alkane, and then the reagents that we're going to use here, so X2, so this is the same X2 of electrophilic addition to an alkene, so bromine or chlorine, all right? So let's put that down here, X equals bromine or chlorine. And something that will become clear as we talk about the mechanism is fluorine we can't use here because it ends up being too reactive, and that's because the fluorine radicals are not stable enough, and so they end up, those reactions just don't happen. And then iodide is not reactive enough, so the iodide radicals end up being so stable that they're just not reactive and they can't proceed through the mechanism. Okay, so bromine and chlorine are the sweet spot of reactivity, and those are the ones we're going to see here. Okay, and so to this reaction, we're going to add some energy, and that energy is going to be in the form of heat or light. Okay, so the way we are going to abbreviate light is going to be H nu, or heat, which we're going to abbreviate as delta. Okay, so this is H nu. Okay, that's how we would say that. Maybe that doesn't make so much sense, but that's nu, the Greek symbol, right? And that represents light. Okay, or we could use delta, the symbol for heat. Okay, so we need one of those sources of energy, either light or heat, and that's going to allow us to initiate the free radical reaction. That's going to give us, the energy to homolytically cleave a bond to generate radicals in the first place. Because if you look at our starting material alkane and our halogen, there's no free radicals. So, the energy to make radicals has to come from somewhere. All right, so what is the product of this reaction? So formally, this is a substitution reaction because we're going to go ahead and substitute our hydrogen for a halogen. And then as a byproduct of this reaction, we generate a molecule of HX. Okay, so notice I went from a hydrogen to a halogen, and then HX is my byproduct. Okay, and so we generated a haloalkane as our product, and then we generated HX as a byproduct. So this is a substitution reaction because we're substituting one atom for another. Okay, so we need to go ahead and introduce the mechanism for this reaction. So, you could imagine, so let me just draw an alkane over here just so I can talk about it. Notice how there's several different types of carbons within that alkane chain. We have some primary carbons here, here, and here. We have a tertiary carbon here in the center, and we have a couple of secondary carbons in between. Okay, so we saw that we're going to replace a CH bond for a CX bond, or we're going to replace a hydrogen for a halogen, but which one of those hydrogens are we going to replace? Okay, and so the mechanism is going to allow us to understand that regioselectivity. Which hydrogen am I going to replace and why? Okay, so let's go ahead and talk about the mechanism. Okay, so the example that we're going to use is going to use methane. And that's going to be so we can avoid talking about which hydrogen we're going to remove, because in methane, we only have one type of hydrogen. It's the hydrogen attached to the carbon, of the one carbon we have. Okay, so we're going to react that with chlorine, and we will use heat. You could have also used light here. Would affect the same thing. And then our product is going to be where we've replaced one of the hydrogens of methane with a chlorine, and then we'll generate our HCl byproduct. Okay, so we break up these free radical mechanisms into 3 distinct steps. Okay, so we're going to talk about the mechanism of free radical halogenation. Okay, and formally they're called a radical chain mechanism. Okay, and they're called a chain mechanism because we're going to see that there is this loop of reactivity we're going to encounter where we're going to take, the product of one of our mechanistic steps and feed it back into the previous step, and we're going to loop around and around and around. Okay, and radical chain mechanisms have 3 fundamental steps. Okay, so all radical chain mechanisms have the same 3 fundamental steps, but what actually happens in each one of those individual fundamental steps will depend on what reaction you're considering. Okay, so the 3 fundamental steps are going to be initiation, and that's where we're going to generate free radicals, and I'll write some of those out, what's happening in each step as we look at it for the above reaction. All right, the second step is then propagation, and this is really the heart of the reaction. This is where we make the major product, and issues of radical stability and various other aspects are important. Okay, and then lastly, we will have termination. That's basically the destruction of any radicals that we made in the process of initiation or propagation. All right, so let's go ahead and look at the mechanism for our methane being converted into chloromethane. Okay, so our first fundamental step is initiation. Okay, so initiation, regardless of what free radical reaction you're considering, is going to be the generation of free radicals. Okay, and generally what happens here is we're going to consider the energy from light or heat. Okay, so light or heat is going to homolytically, or is going to cause, we'll say so, light or heat cause homolytic cleavage of a weak bond. Okay, and we're going to introduce bond association energies or enthalpies, maybe not in today's lecture, but for sure on Monday's lecture, and we'll be able to assess the strength of a bond, and we'll talk a little bit about which bond is going to, how we can rationalize which bond is going to be cleaved in this initiation step. Okay, so in the case of methane and chlorine doing this reaction that we have up above, chlorine ends up being the weakest bond. Okay, so we're going to cleave the chlorine-chlorine bond using that homolytic bond cleavage mechanism we introduced a few minutes ago. Okay, so heat or light, our energy source, is going to initiate that homolytic bond cleavage. Okay, so in this case, we generate 2 chlorine radicals. Okay, so we've generated these chlorine free radicals. So in the initiation step, we've generated radicals where we didn't have radicals before. Okay, and that happens through homolytic bond cleavage. Okay, so now we're ready to move on to step 2. We've generated free radicals, and now we can consider what they're going to do. Okay, so the second step is propagation. Okay, and in propagation, we will have 2 or more individual mechanistic steps. Okay, and in propagation, what we're going to see is, really 2 criteria have to be met. We have to regenerate a radical at the end of the propagation steps, and we need to make our major product of our reaction, or the product of our reaction. Okay, and so in this step, this is where we're going to involve the alkane starting material. Okay, so we're going to think about how does that chlorine radical interact with the alkane. Okay, and so what happens is the chlorine radical doesn't want to have that unpaired electron. So it's going to steal a hydrogen with 1 electron from one of the carbons of our alkane. Okay, and so we've seen what bond breaking looks like in homolytic bond cleavage, but we haven't seen bond making. Okay, so what does bond making look like? Okay, so we represent it in this way. We basically show, the chlorine radical, that electron meeting up with one of the electrons from the carbon-hydrogen bond. That carbon-hydrogen bond has a second electron, and that's going to go to the carbon. Okay, so we're separating the electrons in the carbon-hydrogen bond. One's going to go to the carbon to generate a carbon radical, and then the other is going to meet up with the chlorine radical to generate a bond between chlorine and hydrogen. This is where we're making our byproduct, HCl. Okay, so the products of this step are going to be a carbon radical and then our byproduct HCl. Okay, so we've generated a carbon radical. And so we can rationalize if we have different types of carbon-hydrogen bonds in our molecule, the properties of the carbon radical could dictate which one of those is preferred. So we're going to spend some time on Monday talking about the stability of carbon radicals and what influences carbon radicals generally. Okay, and so one last thing about the step, it has a formal name. So this is called hydrogen atom abstraction. Okay, so abstraction, that means like stealing. Okay, so hydrogen atom is abstraction, that hydrogen's being stolen by the chlorine radical. Okay, so we can see the products of this propagation step. We're not at the products of our overall reaction, so we have to continue on. Okay, so in a second line, we're gonna go ahead and draw our second propagation step. Okay, and so what we're gonna see here is that the carbon radical is gonna interact with another molecule of chlorine, Cl2. Okay, so at this point I should mention, when we were considering the initiation step up here, we aren't using all of the chlorine that we have available to us. This process of homolytic bond cleavage is still not necessarily energetically favorable, but we can force it to happen by introducing an energy source like heat or light. And so that homolytic bond cleavage that we saw up here, is only happening to a small fraction of our chlorine molecules. And so we still have a great, a large pool of chlorine molecules to utilize later on in the mechanism, which now we're at that point in the propagation step. Okay, so now we're going to consider our carbon radical interacting with our chlorine. Okay, so I had mentioned in the propagation steps, there's two things that we have to do. One thing is make our major product. The other thing is to regenerate the radical that we started this process with. Okay, so what does that look like for this reaction? Okay, so we're going to make our major product by basically abstracting a chlorine from Cl2. And so that's going to make, this set of arrows right here is making a bond between carbon and chlorine. And then we're going to, when we separate those electrons in the chlorine-chlorine bond, we're going to regenerate our chlorine radical. Okay. So the products of this step then are our overall products of the reaction. Okay, so this is our reaction product. And then we also regenerate the propagating radical. Okay, so this is why it's called propagating, because we've now created this chlorine radical that can be fed back into the first step. Okay, so we would continue this chain mechanism, this cyclical loop, until we run out of alkane or we run out of chlorine. Okay, and so we would continue this these propagating steps until, again, we've ran out of one of our reagents. Okay, so termination is really, being the third step, is really a minor portion, minor part of this reaction. So, at the end of the reaction, maybe we ran out of alkane. What happens to all those other radicals that are just floating around? Okay, so what happens there is the termination steps, or is termination. Okay, so termination is basically the opposite of initiation. We're going to go ahead and, you probably are laughing at me right now for forgetting to turn off my pointer, but that's fine. Okay, so termination anyway is going to be a reaction that destroys the propagating radicals without generating new ones. Okay, so it's going to be any reaction that destroys propagating radicals without generating new ones. Okay, so we've seen homolytic bond cleavage where we generate two radicals. What would it look like for two radicals coming together? Okay, so there's basically, we've seen two radical species in our reaction up above. We saw carbon radicals and chlorine radicals. So any two of those radicals could come together. So I could have two chlorine radicals coming together. So this is basically the opposite of the initiation step we saw. Okay, so how would that look? It's basically like the two radicals meeting in, in the middle of space or whatever. So that's generating a chlorine-chlorine bond. Okay, and notice how when those two unpaired electrons come together now, there's no radicals in our product of that step. We could also rationalize one of our carbon radicals coming together with a chlorine radical. And this just by chance gives us the same product that we observed in the reaction overall, but this is not where the main proportion or main part of our major product is coming from. That's coming from the propagation steps. These termination steps are just happening with all the leftovers after we've run out of some reagent. Okay, and then lastly, we could imagine two carbon radicals coming together, and that would give us ethane as a product. Oops, forgot the curved arrows on this one, so I'll fill that in. Okay, so we're gonna have 2 carbon radicals coming in together. Okay, and so the product of that is just ethane. Okay, and these don't represent products of our reactions necessarily. We'd call them byproducts, and they are a very, very small fraction of our overall reaction mixture in the end. Okay, so that's where we're going to end today. So we've seen the mechanism of free radical halogenation. What we're going to do on Monday is talk about how we can assess radical stability and what are the trends governing radical stability. And then we'll come back full circle and think about how radical stability affects the regioselectivity of this reaction. Okay, so I hope you guys all have a good weekend, and I will see you guys or talk to you guys all on Monday.